Welcome to the lecture module on optics. So far we have described propagation of light in terms of propagating rays, or we described light in terms of ray optics, propagation of light and the various effects that we have studied so far in the earlier lectures in terms of ray optics. But there are several effects such as interference, for example, which is responsible for color of soap films, the colors that we see, different colors in white light that we see of soap films, or what is known as diffraction or polarization. These are some of the effects which cannot be described by ray optics. And then we have to move on to wave optics, as I have discussed in the beginning of this course module, that whenever there are certain areas which can be discussed by one approach, whereas certain aspects can be discussed by another approach. And so, now we move on to wave optics. So, in wave optics we will, so here it is, wave optics, and let me first discuss the various topics that I am going to discuss in this course. So, here, so the various topics which we will see is, first we will begin with Huygens principle, reflection and refraction of plane waves using Huygens principle. Huygens principle is the first time when light propagation was described in terms of waves. Then we move on to interference. First we will discuss a little bit about superposition of light waves, and then describe the Young's interference experiment in detail, the Young's two hole experiment or Young's double slit experiment will be described in detail. Then we will move on to diffraction, where we will describe single slit diffraction, diffraction by a circular aperture, and we will also discuss the resolving power of optical instruments. And then finally, we will come to the concept of polarization of light, and we will discuss polarization by reflection. There are different ways of obtaining polarized light, but in this course we will discuss polarization by reflection and the Brewster angle. So, before we proceed, we will first discuss some historical milestones which led to the development of wave optics. So, here are some of them which I have listed here. In 1621, Snell gave the Snell's law of refraction, where we knew that it is an empirical relation based on experimental observations. Snell came out with the relation that sin I by sin r is equal to n2 by n1. This we have discussed in detail in the earlier lectures. And then in 1637, the explanation of Snell's law was provided, because Snell's law was an empirical relation based on experimental observation. There was no theoretical support for that. However, in 1637, an explanation of Snell's law was given by Descartes based on a corpuscular model of light, which was later established by Newton, and now it is known as Newton's corpuscular theory. In 1678, Huygens put forward for the first time the wave theory of light, where the propagation of light is described in terms of propagating waves. However, as we will see that Huygens could not answer certain questions such as what kind of waves are these, and therefore, the corpuscular theory prevailed, even though Huygens put forward his wave theory in 1678. For about a century thereafter, the corpuscular theory prevailed. Only in 1801, when Young presented his interference experiment, the two hole interference experiment, which gave a convincing experimental evidence that light is a wave. Of course, subsequently in 1864, Maxwell put forward the theory of electromagnetic waves, and then it was known that light is an electromagnetic wave, which was subsequently experimentally verified later. So, these are some of the milestones to see, and although the Huygens wave theory is no more used in optics, but the development of wave theory, this was the foundation for the development of wave theory. That is why it is a historical milestone. As an historical milestone, we will first discuss the Huygens principle and Huygens theory of light propagation. So, first recall that we will discuss a little bit about what we know about waves and wave propagation. So, here what I have shown is, recall that a plane wave can be expressed as psi of x t, the disturbance, a wave is a propagating disturbance. So, the psi of x t can be represented as a cos k x minus omega t. This k x minus omega t is called the phase term. So, this is the phase and this is the amplitude, a is the amplitude and k x minus